Good morning, guys. Welcome back. Today we're going to start our first day of related rates. And what that means is, well, the word rate, that's another word for derivative. So we're talking about more than one rate, and they are related. Go figure. So here we go. Start with an easy one, although it may seem weird at first. So you have a balloon, and you're inflating the balloon. Well, as the volume of that balloon inflates, more than one thing is changing. The volume of the balloon is changing, the radius is changing, the surface area of the balloon, all of those things are changing. And they are all changing at a related rate, okay? So how do we do this? It'll seem weird for the first one, but just hang in there. As we do a few more, it'll get easier. Okay, first, the word rate is your clue that they're giving you a derivative. So this guy right here, that's a derivative. And if the balloon is being inflated, then they're talking about the volume of the balloon. And these units right here, cubic feet per second, cubic feet, that's also implying volume. So for most of these problems, you need some geometry formulas. So I'm putting a reference sheet on Canvas of all the geometry formulas you're supposed to know, but you could just look them up. So for this one, we're going to need the volume of a balloon or the volume of a sphere. So you look up that formula real quick. Volume equals 4/3 pi r cubed, okay? So that's a formula from geometry that you're supposed to remember, but if you don't, just look it up. All right, so that's the formula we're dealing with. All right, well, we need to get rate in this formula. Well, rate is derivative, so we're going to do the derivative. But for all of these problems, we're going to be doing the derivative, maybe the derivative of volume, with respect to time, because we're going to be talking about how fast this is changing as time goes on. So all of these problems, we're doing the derivative with respect to time, and that denominator tells you that t is the only variable you're allowed to differentiate, and we don't have any stinking t's in this problem. So we're going to do similar to what we did for implicit differentiation, okay? When you do the derivative of a v, you're going to tack on a dv dt. If you do the derivative of an r, you're going to tack on a dr dt. Let me show you what I mean. So the derivative of volume would be 1 dv dt. Literally, this means rate of change of volume with respect to time, okay? On the right side, figure out whether you need a product rule by the number of variables. So on the right side, we really only have one variable, so we don't need a product rule because pi is not a variable, it's a number. It stands for 3.14, blah, blah, blah. So all of this is really just one variable, so we don't need a product rule. So we're going to do a simple power rule. 3 times 4/3 would be 4 pi r squared dr dt. Okay? Basically, every time you do a derivative, you're going to tack on a dt because we're doing the derivative with respect. We did the derivative of an r, which is not a t. Okay, so pretty much every time we do a derivative, we're going to tack on one of those dt's. Okay, I'm going to go a little sideways for a minute. Let's say, for example, we were doing the derivative of this. Maybe there's a number here, okay? If I did the derivative with respect to x when we were doing implicit differentiation, if it was implicit differentiation, then when we did the derivative of a y, that was the only thing we treated differently. So we would have had a 2x plus 2y dy dx equals 0. And that's because we were doing the derivative with respect to x. Well, now that exact same problem, if we did the derivative with respect to time, then same exact problem, doing the derivative with respect to time, the derivative of x squared would be 2x dx dt. The derivative of y squared would be 2y dy dt. That's all, okay? So now we're just going to pay attention to what we're doing the derivative with respect to. And for all of these problems, it's the derivative with respect to time. So pretty much every time you do a derivative, you tack on a dt. Now, what does it mean? What did we find? Back to the problem at hand, over here, this is the rate of change of volume, how fast the volume is changing. Over here, dr dt, That's the rate of change of radius with respect to time, how fast the radius is changing. So those are your derivatives. They are your rates. All right, so now that we have time involved in the problem because we did the derivative with respect to time, we now fill in this moment in time. Don't fill in any of this other stuff until after you've done the derivative. So we read from the top, the balloon is being inflated at a rate of 10 pi cubic feet per second. That's my dV/dt. That's how fast the volume is changing. On the right side, R at this moment in time, because the radius is changing as you're inflating the balloon. So after we get time involved in the problem, we stop the clock and fill in this moment in time. R is 2 right now, and we still have to square that. dr dt is the rate of change of the radius. And that's the question. At what rate is the radius increasing? So this is all we have to solve, and that's actually pretty easy to solve. The hard part for these is figuring out how to get started. But again, with practice, it's easy. I promise you it's not as bad as you might think. Now I got to clean this up. I got a mess going on here. Hold on. Okay, so to continue, we have a 10 pi on the left. On the right, I have a 4 times a 4 pi. So that's 16 pi dr dt. Just get the dr dt by itself. Divide by 16 pi on both sides. And dr dt equals, the pi's cancel, simplify 10/16 and you'd get 5/8. And I want to talk about what that really actually means. Okay, so what does it mean? Well, first of all, this is how fast the radius is changing. And if the volume was in cubic feet per second, then the radius would be feet per second. You want to always write your units. I think it helps you make sense of what you found. And it's a positive number. Since this is positive, it implies the radius is getting bigger. Okay, if you get a negative rate of change, then that thing is getting smaller. So it makes sense. If we were inflating the balloon, then the radius is getting bigger. Now, on your homework, you got to pay attention because sometimes you have to plug in the negative. If they told us from the beginning that this balloon was losing air, then the volume right here would have been negative 10 pi. Sometimes you have to know that. All right, let's try another one. We'll put it all together on the next one. Okay, let's try this one. Take a moment to read it. There's a ladder leaning against a wall. Okay, I'll draw a picture of that. Here's my wall, here's my ground, here's my ladder. Okay. The bottom of the ladder is being pulled away from the bottom of the wall. So this guy is going out. Well, as that's going out, the top of the ladder is going to end up going down the wall. So FYI, this length is getting bigger. So that's going to be a positive rate of change. This length is getting smaller, so that's going to be a negative rate of change. It doesn't have to do with anything about up, down, left, or right. Is that length getting bigger or smaller? All right. Now, a little hint. When you go to write stuff on your pictures, only put numbers on your pictures if they aren't changing. If they are changing as time goes on, then leave them variables. Here's what I mean. The ladder is 25 feet. Is the ladder changing size? Is it suddenly shrinking? Is it getting bigger? No. So I'm going to put that 25 on my picture because it is a constant. It is not changing. But this length down here, as the ladder's being pulled away, that's changing. So I'm going to call that an X. And how fast it's changing would be called dx dt. This guy, this length is also changing. I'm going to call that Y. I don't know where I'm going to fit it. And how fast it's changing would be dy dt. Now, you can pick whatever variable you want, but I always do all of my left rights I call X and all of my up downs I call Y because it just helps me avoid silly mistakes. All right. Now you have to find somewhere in space past knowledge some formula from math that helps you relate these things, the X, the Y, the 25. Well, this is a right triangle. So what could you use from your past to relate the sides of a right triangle? Well, Pythagorean theorem. If there was an angle involved, you could have used right triangle trig, SOHCAHTOA. All right, so we're going to have x squared plus y squared equals 25 squared. And that's the relationship to all the sides of that triangle. Now I need to get time involved. Okay, so to get time involved, I do the derivative with respect to time. So the derivative of x squared would be 2x dx dt. The derivative of y squared, 2y dy dt. And the derivative of a constant, 0. Now we have time involved in the problem. Now you stop the clock and fill in this moment in time. Now I'm going to fill in more info on my picture and more info in my equation. Okay, so now I reread the problem and see what else I have. The foot of the ladder is being pulled away at a rate of 14 feet per second. That's a rate, so it's one of my DTs, I call them. Okay, so it's the foot is being pulled away. So that's dx dt. And that is 14. And you have to take a minute to think again, is it a positive or a negative 14? This length is getting bigger, so it's positive. What other rates do we have? Here's the word rate right there. At what rate is the top of the ladder moving down? So the question is, what is dy dt? That's what they want to know. That's the unknown. And since that's getting smaller, I predict my answer better end up being a negative. Okay, what else do I have? At this moment when it's 7 feet above ground. So at this moment, the ladder is 7 feet above ground. That means that right now this is a 7. The y is 7. Okay, so I'm going to fill in that y is 7. I'm going to fill in all my other stuff. dy dt, that's the question. I don't know what that is. Over here I have a 2. By the way, I could have divided this entire equation by 2 because I just now noticed that you could have. Might have made my computation a little easier. X at this moment, don't know that yet. dx dt, I have that. That's 14. Okay, issue. dy dt is the question, so that's my variable. Well, I can't have two unknowns, so I need to be able to fill in what this x is. Well, look back at the picture. Can you find what x is? Sure, Pythagorean theorem. Basically the same thing we started with right here. So now, after you stop the clock and fill in this moment in time, you can now figure out the other unknowns. Notice we did not plug in that 7 before we did the derivative. Okay? Fill in the things that are changing after you do the derivative, and you fill them in on your picture and at your equation after you've done the derivative. So now do the Pythagorean theorem and solve for x. So 7 squared plus x squared equals 25 squared. So 625 minus 49, square root it. Maybe you remember that's a Pythagorean triple. So after you do the Pythagorean theorem, you'll get that right now x is 24. Okay, so solve for dy dt. Again, it would have been a little easier if I had divided everything by 2 to start with. I could do it now if I really wanted to, but just get dy dt by itself. So subtract this after you multiply it and divide by 14. Okay, subtract the 2 times the 24 and the 14, and then divide by, because we're trying to get dy dt by itself, divide by 14. I intentionally didn't multiply that so I could show you the little trick of you don't always want to pick up your calculator. Look, the 14 is gone. We get a negative 48. And what does this represent? This is how fast, this is dy dt. So this is how fast y is changing. Well, y was this height right here. So the ladder is going down the wall at 48. Let me find the units, 48 feet per second. And we expected it to be negative because it's getting smaller. Okay, so look back through this whole problem because we're starting to warm up now. First, draw a picture. Don't put any numbers on your picture if they are changing as time goes on. The only number we put on in the beginning was the 25 because that wasn't changing. X is a variable, it's changing. Y was a variable, it's changing. Do the derivative with respect to time. Then fill in the moment in time, both on your picture and in your equation. Last, sometimes it's up to you to plug in negative rates. If anything is getting smaller, its rate of change is negative. Okay, let's try another one. Okay, oil is spilling from a tanker, spreads in a circle on the surface of the ocean. Well, that's not good. Okay, we got a circle. The radius of the spill is increasing at a rate of 7 meters per minute. How fast is the area of the spill increasing? Okay, so we have a circle and we have the area and the radius. So I know a formula that relates those. Area of a circle, pi r squared. Okay, I'm not filling in any of these moments in time because all of it is changing. The area is changing and the radius is changing. They're all variables. So we're going to go ahead and do the derivative. On the left side, the derivative of a is dA dt. On the right side, again, we don't need a product rule because pi is a number, not a variable. So it's just a power rule. 2 pi r to the first dr dt. Fill in this moment in time. I got to read all the words now. The radius is increasing at a rate of 7. That means dr dt is 7. If it was getting smaller, I would write negative 7. How fast is the area increasing? So dA dt is the question. Okay. At the moment, when the radius is 15, so right now at this moment, r is 15. So dA dt is the question. 2 times pi at this 2 times pi, sorry. At this moment, r is 15, and dr dt was 7. So just multiply it. So 30 times 7, 210 pi. Now this is area, so it's square meters per second or per minute. That was pretty easy. One more. As we spend more days on this, you'll see that there's actually a lot of good real-world problems, but this would not be one of them. A hypothetical square, whatever, goofy, but here we go. This hypothetical square grows at a rate of this square meters per second. Sorry. Okay, so the units are a hint, square meters per second. So what rate are they giving you? dA dt, the rate of